we're going to be covering energy, heat, and temperature, or calorimetry, and this is information that we covered in class this week. So this should be just a review for most of you guys. So the previous week we talked about the relationship between heat and temperature. And we learned that temperature is indirectly related to heat, but it's not an actual measurement of it. When you use a thermometer, you're not truly measuring heat. So this week we want to focus on how do you relate these two things. And so we have this formula here, which is going to be our relationship between the temperature we measure and the energy or the heat that we either gain or lose. So in this formula, we see that Q equals the amount of energy or heat gained or lost. So Q can be a negative or a positive number. If you've lost heat, then you're going to be a negative number. If you've gained heat, you're going to be positive. So if your temperature has decreased, you're going to end up with a negative number. It's gotten cooler. If your temperature has increased, or you've gained energy, gained heat, you're going to end up with a positive number. M stands for mass, and the unit of that for that is going to be grams. Specific heat is the amount of heat necessary to raise 1 gram of a substance 1 degree Celsius. So you see our unit here, joules, and that's the unit for heat, grams, degrees Celsius, the amount of heat necessary to raise 1 gram of a substance 1 degree Celsius. You could also have your specific heat in calories. So looking back up here, when you're measuring your Q, or you're calculating your Q, Q is going to be either in joules or in calories. Those are the units for that. Delta T, anytime you see this symbol delta, this looks like a triangle, that's going to mean change in. So in this case, we're dealing with the change in temperature. To calculate the change in temperature, you're going to calculate T final, or temperature, or final temperature minus initial temperature. So you can see by this that you could have a positive or negative delta T, depending on if your temperature dropped over the course of the experiment or increased over the course of the experiment. One of the things that we did in class this week is we used calorimeters and did a calorimetry experiment. And a calorimeter is basically a vessel, here's a picture of it, a vessel that has two containers. It has an outer vessel, some type of insulation. In this case, there's an air space. In ours, we used calorimeters that had styrofoam as an insulator. An inner vessel here, and then that's filled with some type of liquid, usually water, and you can have a stirring stick and then you would have a thermometer because you're going to be measuring temperature differences. And we can use this equation here, the calorimetry equation, that negative Q of the object equals the Q of the water plus the Q of the calorimeter. So for example, this week we heated pieces of metal that were unknown, they were an unknown substance, and we heated them to 100 degrees Celsius by putting them in boiling water. Then in our calorimeter, we had water that was at room temperature, so it was around 25 degrees Celsius. When the piece of metal was at 100 degrees Celsius, we took the metal out of the boiling water and dropped it into the calorimeter and looked for the temperature changes. So because of the first law of thermodynamics, where energy cannot be created or destroyed, it can only change forms, whatever energy or heat that the metal lost had to go somewhere, and in this case it was absorbed by the water and also the calorimeter. So that's where we get this equation here. Whatever energy the object loses, it's going to be equal to the sum total of the energy of that the water and the calorimeter gains. So let's look on how you do a problem and do the calculations for a calorimeter equation or problem. So we've got this problem here. A 28.5 gram block of an unknown metal is heated to a temperature of 151.7 degrees Celsius. It is then dropped into a calorimeter with a specific heat of 1.95 joules per gram degree Celsius. and a mass of 5.0 grams, containing 150 grams of water. If the initial temperature of the water was 22 degrees Celsius and the final temperature was 24.2, what was the specific heat of the metal? So one of the things that chemists do a lot is try to figure out an unknown. So that's what this problem is. If we know what the specific heat of a metal is, then we can use that information along with other stuff and look at a table that has characteristics, one of them being specific heat, and go look at it and go, oh wow, the specific heat is that, it may be this metal based on this data. So that's kind of one of the purposes for calorimetry. So when I look at a problem like this, I just look at this, I'm going, there's a lot of numbers here. There has to be a way to organize this. So I'm going to show you what I do. You don't necessarily have to do it this way, but it's just a way to organize your numbers so that you can figure out what information you have and what information you're looking for. So what I do, knowing that I've got two formulas that I'm going to use. Q equals M times C times delta T, and that relates my heat, energy to my temperature. And then I've got my calorimetry equation. Negative Q of the object equals Q of the water plus Q. So I set up a table like this. I divide it so that I know for everything, for the metal, the water, the calorimeter, I need to find a Q, a mass, a specific heat, a T final or final temperature, and a T initial. And so I just started my problem up here, a 28.5 gram block of an unknown metal. Okay, well that goes in the metal category, and that's a mass, so I'm going to put this here under the mass. It's heated to a temperature of 151.7 degrees Celsius. Well, here's 151.7. That's my initial temperature of my metal. It's then dropped into a calorimeter with a specific heat of 1.95. Well, that goes under my calorimeter category, 1.95, right there, under specific heat. And a mass of 5 grams. Okay, calorimeter once again, and here it is, 5 grams. Containing 150 grams of water. Okay, I need to find my water category, and I put this under 150, or under my mass. There it is, 150. If the initial temperature of the water was 22 degrees, okay, so that's the initial temperature of the water right here, but that's also going to be the initial temperature of my calorimeter, because if my water is 22 degrees, that's sitting inside the calorimeter, so the calorimeter has to be the same temperature. And the final temperature was 24.2. 24.2, that's my final temperature of water. It's also going to be my final temperature of the calorimeter, and it will also be the final temperature of the metal, because when that metal is dropped in the calorimeter, whatever the final temperature of the water is, that's going to be the final temperature of the calorimeter and the metal. So T final is always going to be the same thing all the way across. What is the specific heat of the metal? Well, there's my unknown. That's what I'm looking for. So I look at this chart and I'm going, okay, well, with my metal, I've got two unknowns, so I can't really do anything there at all. But look, with water and calorimeter, I've only got one unknown, and that's Q. So I can calculate the Q for the water and calorimeter because I've got all the information necessary to do that. I just need to plug in numbers. And it doesn't matter which I start with my calorimeter. So the Q of the calorimeter is equal to M times C times delta T. So I'm just going to plug in my numbers here. My mass was 5, my C was 1.95 joules per gram degree Celsius, and my delta T, remember, is T final minus T initial. So I need to ask myself, does this make sense? Should I have a positive delta T? Well, yes, I should, because my calorimeter is going to be gaining heat energy from the metal. I also want to see a positive Q because, once again, we're gaining energy. So in this case, I get the Q of the calorimeter as 21 joules. You notice this is only two significant figures because if I look at my numbers up here, my mass is only two significant figures. So that's as far as I can take that. So once I figured out that, I'm also going to figure out the Q of the water. Same formula, Q equals M times C times delta T. I'm going to plug in my numbers, but this time I'm using the water. So I've got 150 grams. My specific heat of the water, this is a constant. You need to remember this. You notice it wasn't in the problem itself, but you should know that the specific heat of water is 4.184 joules per gram degrees Celsius. This delta T, T final minus T initial. Delta T in this case is 24.2 minus 22. Once again, ask yourself, does it make sense? I want a positive Q because I know my water is gaining energy. To get a positive Q, I have to have a positive T. And so 24.2 minus 22 is going to give me a positive delta T. So I end up with the Q of water at 1400 joules. So now that I'm there, I can use that information because now I know the Q of the water and the Q of the calorimeter. The sum of that, or how much energy the water and the calorimeter gained, is going to equal how much energy the metal lost. So I've got my negative Q of the object equals 1400 joules plus 21 joules. And that's going to give me the Q of the object will be negative 1421 joules or negative 1400 because of significant figures. Remember the calorimeter, I can only go to 2 significant figures. Okay, so now you'll notice on my chart here, I went ahead and put the number of joules under the calorimeter, the number of joules that was gained by the water, and then here's the number of joules that the metal lost. And now that I've got that information, I've only got one unknown, and I can solve for my unknown. So I'm going to use the same formula that I've been using all along, Q equals M times C times delta T, but I'm going to rearrange this because my unknown in this case is the C, or the specific heat. So C equals Q of the metal divided by mass times delta T. I just got that by dividing this side by mass times delta T. Whatever I do on this side, I have to do on this side. So that's where that number came from. So now it's just a matter of plugging my numbers in. Negative 1400 joules divided by the mass, which was 26.5, times my delta T. Remember, delta T is T final minus T initial. This is where most students make their mistake. So ask yourself, does it make sense that I have a negative delta T? Did my temperature go down? Yes, it does. It also makes sense because you have a negative energy here, or a negative heat. You cannot have a negative specific heat. So I need to have something that will cancel out this negative sign here. And that's where this negative delta T comes from. I end up with a specific heat of 0.39 joules per gram degrees Celsius. Another way to double check your work is to ask yourself, does my specific heat make sense? Specific heat is usually, for metal, is usually under 2. There's certainly some exceptions, but it usually is. Water, with its 4.184 joules per gram degrees Celsius, is a relatively high specific heat. So if you put your numbers in and you're getting something like 26 or 27, revisit your math, okay? Because you've probably made a mistake. Once again, you don't have to use the chart if you don't like it, but you do need to show all your work. I want to see all the steps of the problem. I don't want just a final answer because I want to be able to see that you understood what you were doing. So I hope you guys enjoyed this recording. I hope this helped a little bit. And as always, if you guys have any questions, don't hesitate to email me or give me a call. Thanks. I'll see you on Monday.